Hello there, and welcome to the fifth in a series of videos about reaction dynamics for the module CHE30042. So today we're going to be talking about transition state theory. We've already covered collision theory and we've looked at potential energy surfaces, and transition theory is basically taking some of the stuff from both of those aspects and putting it together. Okay, what we're going to do today is introduce what transition theory is and also derive the equation, and in the next video, which will also be available this week, you have the opportunity to we're going to go through the application of transition state theory and see how effective it is at making predictions. In terms of additional reading, there is the usual sort of thing. So there's a limited amount of information in elements of physical chemistry, and this will hopefully take you directly there, the QR code, if you scan it into your phone. There's also a bit more information in this reaction dynamic kinetics book. But as I said already, that's available in the library, and also it is available online, but in a limited sense. So I said right in the introduction, this QR code here takes you to a website that houses this book as an ebook, and that you can sign up to for just a couple of weeks for free. So I'd maybe hold fire on signing up for that website just now, and maybe do it and have a look at it all in one go at one point in time. Finally, I was looking for some other information you might have to support your learning, and I came across this online book chapter, which is Introduction to Transition State Theory. This actually goes through the derivation of the equation in much the similar way to the way we're going to go today. So yeah, I would encourage you to maybe have a look there, because it's another way of obviously reading something compared to me going through it. Okay, so that was quite a long introduction. We're going to move on to the content now. So transition state theory, this is also known as activated complex theory, as it says on the slide, and this really here is the key reaction. Okay, so you've got, again, we're doing our reaction of A plus BC goes to A, B plus C, but transition state theory puts these two steps in. So it says that the reactants are in equilibrium with a transition state, which is this X with the double dagger sign here, and that then once that's made, then there's a reaction that takes it to the products. Okay, a key point about this state is this is not an intermediate state. This is a transition state. It's unstable and with a very short lifetime, as stated here. And you're familiar with looking at this activated complex or this transition state, and you may have written out mechanisms or seen mechanisms with such a thing in it, because organic chemists will use these in their mechanisms to sort of explain how things are going to go through. And also, every time you draw a reaction coordinate diagram and you have a high point here, this is the transition state, okay, and this is the activated complex. So the activated complex may look something like this, where A, B, and C are all bonded together. And then, of course, this bit is in equilibrium with each other, and once you get here, you then have a straight line towards the products. That's what transition state theory says. And again, you can see that on a potential energy surface in much the same way as you can on reaction coordinate. The only thing about the potential energy surface is that we can actually get information out. So for example, on my mouse dot there, that can actually tell us what the distance between A and B is, and the distance between B and C, so we can get an idea of the bond length. And we can say that, well, neither bond length in this case has increased dramatically. They've both increased, but not increased dramatically at the transition state. Whereas if the transition state were here, you might say, well, the BC bond is much bigger, whereas the AB bond is actually pretty similar to how it would be at the end. Okay, so we can start using the transition state diagram and how it looks to give us some information about our reaction. Okay, of course, the other thing we can get from here is the activation energy, and that is essentially the difference in energy at the transition state and the reactants, right? And likewise here, you can say, well, it's the difference between the energy here and the energy here. Okay, so let's sort of think about deriving this equation. We've got our general reaction, and I've now explicitly put in an equilibrium constant for this equilibrium process here and a rate constant for this process here. Okay, so as I said already, this transition state is in equilibrium with the reactants, so we can write an equilibrium equation as I have done here with the products on the top and the reactants on the bottom. And of course, we can rearrange this to give us this equation here, and you'll see why this is important in a minute. Okay, so we can say that the rate for this equation here, so the rate of formation of products, is given by the concentration of this species multiplied by the rate constant for this reaction. Okay, so that's just written here. And, you know, if we substitute this in place of the concentration of this species, which is obviously probably going to be pretty low and difficult to measure, yeah, then we can get this equation here. So we're sort of on our way towards some sort of idea of how we might calculate the rate, albeit with two things we can't currently measure. The overall rate equation, however, is still rate is equal to second order rate constant times by the concentrations. So of course, well, we now know that K2 within transition state theory is equal to this rate constant here times by this equilibrium constant here. Okay, so that's what I've written here on the slide. So key point is obviously that in order to develop our transition state theory and derive it, we need expressions for both of these things. But once we've got those expressions, we can actually get an idea of how we can calculate the overall rate or the overall rate constant, yeah, just as we did for collision theory. So it takes us back to actually thinking about potential energy surfaces again, and we need to go back to thinking about this idea that using potential energy surfaces we can actually see vibrations occurring. Okay, and so we said that if we had a motion that was like from a transition state, if we have a motion backwards and forwards like this, when we go to here, then both A and B are becoming smaller, and when we go to here, both the radius A and B and the radius BC are getting bigger and getting smaller, so it's going effectively moving in and out, yeah, and so this is a symmetrical stretch as I've depicted up here. Likewise, if we have a motion in the opposite direction, if we move this way, then our AB radius, or the distance between A and B, is getting bigger, but the distance between B and C is getting smaller. So in this case, we have our asymmetric stretch like this. Yeah. Okay, so depicted up there. So this kind of motion is an asymmetric stretch. And of course, the key point here is that motion from the reactants to the products, from the transition state towards the products, the motion is effectively an asymmetric stretch, isn't it? Because it's going in that direction, not along this line here. Okay, and that's a key point. So when we're thinking about the rate, we're thinking about the frequency at which this process occurs, this asymmetric stretch. Okay, because obviously this asymmetric stretch is going to lead to a formation of a bond here and a breaking of a bond here. Yeah. Okay, so that's the key point, which is that this one asymmetric stretch is going to account for the transition state going to the products. Now, key point is that this doesn't have any energy barrier because it's just already happening, okay? And so it will give products every single time. And the key approximation that transition state makes is that you can't go back once that bond's been broken. Okay, so it says that the reactants are in equilibrium with the transition state, but not the products with the transition state. Okay, so we can write the following expression, which is essentially what I just said, that the rate constant is going to be given by the frequency of the vibration of this actual stretch. Okay. We have to add in something else, which is this idea of a transmission coefficient. And this transmission coefficient is effectively how good that vibration is at yielding the products. So, you know, will it always fully lead the products, or will it sort of be not quite floppy enough to always lead to the products? Will it sort of sometimes come back? Now, basically what we do for transition state theory and forevermore, we're going to assume that kappa is equal to 1. So every time you're doing a calculation transition state theory, we assume kappa is equal to 1, and that means that every time this vibration occurs, we get products. Okay, and so what we can do is we previously had an equation that included this times by the equilibrium constant, so the rate constant times the equilibrium constant equals K2, and now in that place we can put kappa times the vibrational frequency of that stretch. Okay, and we stay here for now. All right. So don't forget this point. Okay, and of course, yeah, this is better because we now have a bit more understanding of how we might get this number, but obviously we still don't know this number and we still need to get some more expressions. So we still need to do some work here. Okay, now let's delve into the other one. So we've sort of partially sorted out the rate constant. We now need to think about the equilibrium constant. And in order to do that, we need to think about molecular partition functions. Now, going back to some of the material you learned in 20059, or 20,059. You learn from Rob that a partition function for a molecule is giving an idea of how many energy levels are occupied, okay? And of course, that's going to be temperature dependent, and at higher temperature, you've got more energy levels available. So, that's depicted here on the graph. So your partition function is low at low temperature, and it gets bigger at higher temperature, and therefore more of these energy levels are occupied, okay? And of course, Rob also said that this molecular partition function is going to be a product of multiple partition functions, each for an individual energy level. And we sort of already know that energy is divided into multiple different levels within a molecule, and so you've got things like electronic energy level, vibrational, rotational, translational, and all of these multiplied together are going to give the full partition function. Okay, and the final thing that Rob introduced in his notes, and if this is all kind of feels new to you, then I really would encourage you to go back to those notes from last year. But the final thing is basically that if you know the partition functions for your molecules, you can actually draw up an equilibrium constant. Okay, so for the reaction like this, and this is obviously very similar to the reaction we're looking at, we can say the equilibrium constant is equal to the partition function of C divided by Avogadro's number, divided by these two here. So this is just the reactants partition functions, and they have to be multiplied together, each divided by Avogadro's number. And then you've got this exponential term here, where this part of the exponential term is that energy difference between our products and our reactants. Okay, and so as Rob said in his notes, that's not necessarily the activation energy. Okay, although actually in the transition state theory case it kind of is. Okay, so to apply what we now know, you just remember this general reaction that I copied from a previous slide. We've got A plus BC, which is in equilibrium with our transition state and then leads to the products, okay? And the key point is that when we're going to evaluate the equilibrium constant, the reaction we're looking at is this part here, okay? The part I'm boxing. And of course, the reactants are A and BC, but the products are the transition state, not the actual products, okay? So, and that's a really important point, because that will determine what the equation we use is. We can then put the equation together, and it's very similar to the one I showed on the previous slide, because we basically have two things reacting together to give one thing. So it looks exactly the same. I've just changed the subscripts essentially. Okay, so we've got we're now using the partition function for the transition state, and we've got the partition function for the reactants down here. The other change is here, okay? So this is the difference in energy between the products and the reactants, okay? And in this case, it's obviously very similar to the activation energy, as I suggested on the previous slide. So we've got this expression for our equilibrium constant, and therefore we can sort of start building this into the equation. So if we remember that this from a couple of slides back, we had this term, then we can basically essentially rearrange this equation. We can cancel the L, so 1 over L divided by 1 over L is cancels, so these two cancel, and 1 over L is equal to L, so that's where this one comes from. Okay, and we just literally substitute this in for this, okay, and we end up with this equation here. Okay, so this is already starting to look an awful lot like an Arrhenius equation, because you've got a pre-exponential factor here and an exponential factor, but it also sort of, just as collision theory did, so we had an exponential factor and a pre-exponential factor, right? So we're still a little bit far away because we're not quite sure how to get these and not sure how to get these, but we're getting there. Okay, just as a brief aside, I just wanted to go explain the origin of L and show you that these equations are going to be different depending on the type of reaction we're talking about. So transition state theory doesn't just need bimolecular reactions. We can talk about unimolecular reactions, and we can also talk about termomolecular reactions. In each case, we have a different presence of the Avogadro's number within the equation. Okay, so you can see it here. So we've already explained the bimolecular one. Obviously, if it's unimolecular, then you have one species going to a transition state, and just the 1 over L's are both going to cancel there, so we're not going to have it here. And finally, for termomolecular, which you can probably have a guess about why this is very unlikely, but this is where three things simultaneously hit together to make a transition state. Yeah, just think about how many times you bumped into two other people simultaneously. But that one there has a sort of Avogadro's number squared term in this equation, and you can prove it to yourself, but it's essentially because there's another one here. All right. Okay, so just to jump back again, sorry for the aside, but basically we've got this expression, and the key point here is that this is using molecular partition functions. As I said a couple of slides back, each of those molecular partition functions is going to be a product of the partition functions for each type of energy level, and as you learn with Rob, these can be calculated. Okay, so we've got expressions to calculate each of these that I'll show you on the next slide, and the really important point here is that this allows transition state theory to account for molecular complexity, because obviously the bigger the molecule, or the more atoms a molecule has, the more of these partition functions it's got. If it's just one atom, it's only going to be able to translate. It doesn't do any vibrations because it's one single atom. Whereas if it's got multiple bonds, it's going to have lots of vibrations, okay? And it'll have rotations too. So you're going to get different behavior for those different types of molecules now that collision theory couldn't take into account, but transition theory does. Okay, so just to talk about these partition functions, we've got, and this is a bit of revision from Rob's course, but there's a few other things we need to take into account too. Okay, so you start with translational partition functions, and the 3 here in this translational thing indicates you can move in 3 dimensions. Okay, and that's always the case, of course. So this takes up 3 degrees of freedom. Okay, and I'll explain what that means in a minute. Okay, but you should already be a little bit familiar with how many degrees of freedom a species has. And the other thing that's important is the magnitude this is a magnitude at around about room temperature, and these are things you need to be able to sort of remember essentially. And so this translational partition function has a magnitude of about 10 to the 33 per meter cubed. Okay, rotational. If you have a linear molecule, and this is a properly linear molecule, and I'll give you a couple of examples of that, but for example, CO2 would be a linear molecule. Okay, and some very basic alkynes are linear molecules, or bimolecular, diatomics would be linear. In this case, this is given by this expression here. It's 2 degrees of freedom because it's linear, and its magnitude at 300K is about 10. If it's a non-linear molecule, and this is most molecules, to be honest, then it's 3 degrees of freedom because it can rotate in all dimensions, and it's got a magnitude of about 100. Okay, and then basically any other degrees of freedom would be vibrational or would be taken up with higher energy levels. Okay, so electronic energy levels, we're not really talking about transitions within electronic energy levels here because the energy required to do that's pretty high. So we're generally just going to talk about these 4 types. And of course, there's also spin, partition functions, etc. The key points here are the magnitudes again. So we always assume that the vibrational partition function has a magnitude of about 1. Okay, and the electronic at room temperature, electronic partition functions is also 1. The other important point on this slide is the temperature dependencies of these. So for example, the translational partition function is proportional to T to the 3/2. Rotational linear is proportional to T. Non-linear rotational, T to the 3/2. And again, 3 dimensions, 2 dimensions. And the vibration, well, we just assume this is equal to 1. Okay, so that would be the temperature dependencies. And again, you're going to need those in order to apply these things later on. Okay, so I've been talking about degrees of freedom, and here's where we sort of learn a bit more about that. Okay, so I think you should already know that in terms of the number of degrees of freedom you've got, that's always given by 3n, where n is the number of atoms. So for example, for a diatomic, you'd have 3 times 2, which is 6 degrees of freedom, 3 of which are going to be translational, 2 of which are going to be rotational, because a diatomic is always linear, and the 1 remaining degree of freedom with vibrational, because of course it's a diatomic and it can vibrate. Okay, the next part to that is the ability to then write a molecular partition function of that, and in this course this is how we're going to do this. We're going to write the molecular partition function as equal to the translational one where x is equal to 3, the rotational one with 2 or 3 depending on whether it's linear or non-linear, and of course it will be 0 or non-existent if you've just got a single atom. And finally, Z for the vibrational one, where Z is the remaining degrees of freedom. So I'm just going to go through a couple of examples of this, and I'm going to put a few examples in the quiz that you can practice with. Shouldn't hopefully be too difficult, but this is the foundation of doing any of the sort of applied transition states theories kind of thing. So I need you to be able to get, understand this. Let's just start with this one here. We have 1, 2, 3, 4 atoms here. So in that case, we have 3n, which is, so that's 12 degrees of freedom. It's a linear molecule, so it's got 3 translational degrees of freedom. It's got 2 rotational degrees of freedom. And how many vibrational degrees of freedom it's got? Well, it's got 7. That's the remaining, isn't it? So we can write that down here: trans, rot, vibrational, yeah, and we can then write our molecular partition function, and it looks like this. Now, key point here is that these little numbers here, these are not powers. They're just basically being used to remind us how many degrees of freedom are available here. Okay, so if we were to approximate the order of magnitude of this partition function, we'd say it's 10 to the 33 times by 10, so that's 10 to the 34 times by 1. Okay, so it's going to be about 10 to the 34 per meter cubed. Okay. But yeah, and so we'll do a bit more of that in the next screencast. Okay, I'll just go for another example here. So we've got, in this case, a non-linear molecule here. Again, it's got 3 translational degrees of freedom, but it's got a lot more atoms here. So don't forget the hydrogens. You can basically count all the hydrogens too, and you end up with 18 atoms. So the total number of degrees of freedom is 54. Shouldn't really surprise you that this molecule can vibrate in a lot of different ways. Okay, so having 48 different vibrations makes sense. It's got 3 rotations because it's non-linear. Okay, so it's it may have some symmetry, but it's still non-linear. Okay, so and this is how you'd write this out. Okay, so hopefully that's pretty clear. So moving back, we said that we had one bond vibration in the transition state that leads us to the products. Okay, and so obviously if we're thinking about understanding the transition state and understanding the partition function for the transition state, well, we can write the expression for the partition function for the transition state in much the same way as we did just for those 2 molecules, reactants. Yeah, if we know what the reactants are, then the transition state is just going to be the 2 things added together. Okay, but the key point about the transition state is one of the degrees of freedom in it, which is a vibration, and it's actually specifically it's a asymmetric vibration, is the one that's going to lead us to the products. And this one is the one that we've already sort of talked a bit about. Yeah, we've got a partition function. We can just write a partition function for that particular vibration, and this has just come straight out of the table I showed you before. And as you can see here, this is going to be somehow related to the frequency of the vibration. And this is important because obviously we've got that frequency of vibration in the equation that we aren't really sure how to get rid of, and I'll show you here that we can get rid of it pretty straightforwardly. Okay, because the nice thing about this equation here is that using a Taylor series expansion, this simplifies to this. And if you want some confirmation of that, you can go to the QR code here. This leads you to elements in physical chemistry, which sort of shows the same thing happen. Okay, so this now can be exchanged for this, right? And of course, within the transition state, within its partition function, the partition function for the transition state is basically the partition function for this one vibration multiplied by all of the other partition functions, or all of the remaining degrees of freedom within there. So this would be every other type of vibration it can do other than this one, plus any rotations or translations. Okay, so if we write this like this instead of like this, then we can put this into our equation, and I'll show you how to do that on the next slide. But basically what we can do then is we can actually remove our frequency of vibration, which is something we don't know, from the equation that we're building up, which is kind of handy actually. Okay, so we've got these relationships. This is an equation I showed you a few slides back, which still had this in it. We now know how to calculate these. We can do that by using the equations I've shown you already. Okay, and we just learned this one from the previous slide. So in place of this, we can now put this. When we do that, we get 1 over the frequency on the top here, and these 2 will cancel, and that leads this equation here. Now, this equation is very important. This is called the Eyring equation. It's one form of the Eyring equation, for the rate constant, okay? And the key point is when you use this equation, if you use everything in SI units, you've got the answer in meters cubed per mole per second. Okay, and the key point there, of course, is through this term here, we're allowing for molecular complexity. We've got an exponential term here. All of these things we can measure. These are all constants. Is Planck's constant, is temperature, Boltzmann constant. This one's equal to 1. We can calculate all these because it was all constants within there. That's Avogadro's constant, and this is something to do with the activation energy. Okay, so we have a very similar equation to Arrhenius theory or to collision theory, and in the next group screencast we'll look at how we can actually apply that. So thank you very much for listening, and I'll tune off now.